This video is brought to you by PPLIR Europe, a not-for-profit community of European general aviation pilots dedicated to helping ourselves and others to use our licenses to the full. We share our passion for flying through mutual exchange of expertise, experience, information, inspiration, and education. We also assist regulators in framing legislation that affects all GA pilots. We're almost all volunteers and do it because we love it, though we do also need to raise a little money, mainly to fund our representation and lobby activities. Please join us, improve and broaden your own flying, enjoy belonging to a community of like-minded pilots, and help us represent you. Hi, this is the second in the series of instrument flying videos I'm making for PPLIR Europe. In this video, I'm going to focus on tracking and intercepting, covering NDB, VOR and GNSS, whether on an RBI, RMI, OBS, HSI, or on a glass eHSI. The techniques of tracking and intercepting a track are much the same for any aid, but the interpretation of the instruments is quite different. Initially, I will briefly discuss the navigational aids, explore the interpretation of different instrument presentations. Then I'll talk about tracking and finally techniques for a neat interception. So let's talk first about the different presentations. The non-directional beacon, or NDB, represents the earliest attempt to use radio to navigate. But for today's GA pilot, the NDB is truly legacy technology. The equipment in the cockpit is useful to listen to your favorite AM radio station, but its use as a navigational aid is largely restricted to the initial IR skills test. The required equipment also represents a waste of panel real estate, both for the box itself and the indicator. So much so that a decision to retain the ADF in place of, say, an accurate fuel management system represents an increase in overall risk. There are just so many better ways to make your flight safer. There's a little confusion about terminology because the radio beacon on the ground is called an NDB. The receiver in the aircraft is an AM radio called an automatic direction finder, or ADF, and which uses a directional aerial to determine the direction of the signal from the NDB. And that direction is presented to the pilot as a single pointer or needle. The instrument it is displayed on is the RBI or RMI. The simpler and less usable presentation is called the relative bearing indicator, or RBI. The RBI has a manually adjustable card behind the pointer, marked with compass cardinal points and degrees. This card can be manually aligned with the aircraft's direction indicator or compass. However, most instructors recommend that it is left static with north at the top, and the relative bearing transposed mentally onto the DGI or HSI. The workload of continuously moving the backplate to align with the heading is too great and is often forgotten, leading to disorientation and confusion. A refinement of the RBI is the radio magnetic indicator, or RMI, where the card behind the needle is connected to a remote magnetic sensing source and automatically rotates, staying continuously aligned with magnetic north, so that the magnetic direction of the aircraft to or from the NDB may be read directly from the instrument, eliminating the need for manual alignment with the direction indicator or compass. Tuning is by entering the frequency into the ADF equipment, normally by means of rotary knobs. ADFs normally can only tune to the nearest kilohertz, though some NDBs are set to 0.5 of a kilohertz. In that case, tune to just above or just below, picking the frequency that seems to work better. NDB carrier transmissions are overlaid with a 2- or 3-letter Morse code identification, usually referred to as an ident. The audio from the ADF equipment is normally routed through the aircraft audio panel, thus when selected on the audio panel, the Morse identification can be heard. There is, however, no other means to alert the pilot to a failed NDB transmitter or indeed failed ADF receiver. So, if you're using the equipment to fly an approach, it's a good idea to be listening to the Morse faintly throughout the procedure to ensure the equipment hasn't failed without warning. Along with the poor accuracy and errors inherent with NDB use, continuously listening to repeated Morse identification during the busy approach flight segment is distracting and reduces pilot mental capacity. Historically, some NDBs were broadcast without an audible Morse ident, but needed a beat frequency oscillator or BFO to be heard. That is why most ADFs have a BFO switch, but I've not come across such NDBs for many years and don't think there are any that still exist in Europe. There is an ADF and/or test function on ADFs that allow the needle to move to a test position, normally a relative bearing of 090 degrees, i.e. the starboard wingtip. This permits the pilot to confirm that the needle moves actively from its test position to point at the NDB, thus eliminating the possibility of tracking a mechanically stuck needle. Some ADFs also pick up a better identification signal when in ANT mode. Having tuned, identified, tested by deselecting and reselecting ANT to allow the needle to point at the NDB again, you should check that the direction indicated is sensible. Before use, you should check the range of the NDB and ensure you do not try to use it outside of the safe range. Before talking about tracking, let's discuss the other radio navigation and cockpit presentations. Both VOR and GNSS signals may be presented as a single needle pointing directly to the VOR or GNSS waypoint, but they are more usually presented in the cockpit on a course deviation indicator or CDI. A needle, or in the case of a horizontal situation indicator, eHSI, the center section of the needle, which moves side to side to indicate how far off the desired track the aircraft is. The desired track is selected either by aligning the index with the required compass point on the Omni Bearing Selector, OBS, ring, or setting the pointer of a horizontal situation indicator, or HSI. On an OBS, a revolving card graduated with degrees and cardinal points is turned by a small OBS knob so that the desired track is at the top of the instrument, aligned with the index. On an HSI, the backplate is driven by a remote compass and gyro to always show heading, but the desired track is selected with the course pointer. Thus, the HSI is superior to the OBS because, in addition to the desired track and deviation from track, it also shows the angle between the heading and desired track, giving an intuitive overview like an early moving map. I'm not aware of electronic OBS indicators, but electronic HSIs, or eHSIs, are now very common. Because they're presented on screens, they're colloquially known as glass. The biggest two operational differences between an HSI and an eHSI is that on the glass instrument, the course pointer and CDI generally turn automatically to the desired track. This is called auto-slew. And the track pointer, the small colored diamond, which can move around the eHSI compass rose, shows the actual track flown, not to be confused with the course pointer, which shows the desired track. VORs differ from NDBs in that while NDBs broadcast the same signal in every direction, hence the non-directional bit, VORs transmit different signals in each direction. If the aircraft is on the 090 radial from the VOR, that is what it will show, regardless of its heading or orientation. The same is true of a GNSS track, and that is why the two can be displayed on the same instrument. Sticking for the moment with the use of the OBS or HSI to present VOR information, once the VOR is tuned and identified, and within its designated operational coverage, DOC, and with no nav-flab flowing, in a similar way to that described earlier for the NDB, the OBS card can be turned so that the course deviation indicator, CDI, displays the deviation from the track aligned at the top of the card, or the HSI is turned to show the CDI deviation from the selected track shown by the pointer. As the OBS or HSI is moved to different tracks to or from the VOR, the deviation is displayed by the CDI moving left or right of center. When tuned to a VOR transmitter, each CDI graduation, or dot, represents 2 degrees left or right of the selected track. Given that there are 5 dots either side of the center of the CDI display, only deviation information up to 10 degrees right or left of the selected track is displayed. Thus, the OBS or HSI needs to be turned to align the CDI approximately with the middle of the display, plus or minus 10 degrees, before an accurate track may be read. The same presentation is used for the Instrument Landing System, or ILS, but in this case, the localizer final approach track is represented by the CDI centered and the OBS is disabled. The CDI is much more sensitive to deviations for the localizer beam. I'll be discussing this in my next video. Some OBS and HSI displays have 4 dots either side of the center, with the first dot represented by a large circle. See the difference between the OBS display, the center circle plus 4 dots each side, and the HSI. Very often, eHSIs have only 1 or 2 dots each side of the center. In these examples, both instruments are set on the 330-degree radial from a VOR, and both are showing 3.5 dots or 7-degree deviation to the right. This could be read as I'm on the 330 minus 7 equals 323 radial, but a more common reading is I must turn right to get onto the 330-degree radial. Indeed, that heading to the right is shown on the HSI. There's no way of seeing what your heading is on the OBS alone. The display incorporates to and from flags to inform the pilot whether the display is tracking to or from the fix. Also, unlike the RMI and RBI, the instrument displays a warning flag if a VOR signal is not received when tuned or is lost during operation. Lastly, in the previous examples of the OBS, the CDI moves vertically left and right in the horizontal plane, but on the older designs it's hinged at the top and the CDI swings left and right. When discussing the VOR, I said that the deviation is graduated in degrees left or right of the selected bearing, i.e. an angular off-track error. So these indicators are showing that we are 0.6 of full scale deflection, 6 degrees, to the right of a 270-degree radial. Using the 1 in 60 rule, that means that at 10 nautical miles from the VOR, we're 1 nautical mile to the right of the selected radial. But at 20 nautical miles, we're 2 nautical miles to the right. Another way of describing this is that the sensitivity is increased near the VOR and decreased further away. But if you're using a GNSS source, such as GPS, the OBS or HSI displays the deviation left or right of track in nautical miles. Any deviation from the track calculated by the GNSS receiver is displayed on the CDI as a cross-track error, or XTE, each dot representing an actual distance. The distance represented by each dot is dependent on the segment of flight, i.e. en route, terminal, approach, missed approach, etc. But if it's in terminal mode, as in this example, full-scale deflection is 1 nautical mile, so 0.6 deviation is 0.6 of a nautical mile, and that is equally true close to and distant from the waypoint. For GNSS waypoints, note that the orientation of the OBS or HSI course pointer makes no difference. The aircraft is 0.6 nautical miles to the right of track, taken from the flight plan, or perhaps direct to track from the navigator, and that will be displayed on the CDI regardless. This is in contrast to navigation with respect to a VOR radial, which must be chosen. It's good practice to turn the OBS to the desired track for reference. You can use a GNSS receiver to set any course inbound to the next waypoint by pressing the OBS button. This causes a GNSS waypoint to behave much as a VOR, at which point the OBS on the display instrument becomes active again. This is particularly useful for lining up with runways or for setting up holding inbound tracks. However, the CDI will still indicate cross-track error in distance, not degrees. So if you use it to find a runway and leave the GNSS in terminal mode, the accuracy approaching the runway is half a nautical mile off at half-scale deflection. To put that in context, this is a scale drawing of a light aircraft approaching a typical 800 by 25 meter runway with half-scale deflection. So if you're going to use this technique, you need to put the GNSS into 0.3 nautical mile sensitivity and fly very accurately. In the glass cockpit, the pilot is given autonomy to decide how they wish to display the chosen track to or from a GNSS waypoint, either as a single needle in the same vein as an ADF needle, a CDI or HSI showing cross-track error, or a mixture of all overlaid on a DI. If the waypoint is a VOR, the display will be as for a normal VOR. Displaying cross-track error is very useful when the CDI displays full scale. Partly because the pilot has so much choice, glass cockpits provide ample opportunity for pilot cock-ups, and training is necessary to avoid any "what's it doing now" moments in the air. So, now I've talked about the various ways the tracking information can be displayed to the pilot. Let's go back to talking about tracking. Regardless of the display technology, having selected the required track, accurate tracking requires the pilot to lay off the effect of wind. So let's talk about that first. The maximum wind drift occurs when the wind direction is fully abeam. A reasonable approximation of maximum drift is given by dividing the wind speed by the true airspeed, TAS, expressed in miles per minute. Hence, at 120 knots, the aircraft is flying at 2 nautical miles a minute. So when experiencing a 20-knot crosswind, the maximum drift will be approximately 20 divided by 2, or 10 degrees. Or at 90 knots, the aircraft is flying at 1.5 nautical miles a minute. So when experiencing a 15-knot crosswind, the maximum drift will be approximately 15 divided by 1.5, or again 10 degrees. Of course, the amount of crosswind will vary as the angle of wind off the nose or tail varies. And to simplify this, some people like to use the watch face method. You think of the number of degrees the wind is to your track and translate that into minutes as a fraction of an hour. So 15 degrees off is 15 minutes, quarter of an hour, so a quarter of the maximum drift. 30 minutes is half an hour, so half the maximum drift. 45 minutes is 3/4 of an hour, so 3/4 of the maximum drift, and anything over 60 is a whole hour, so all of the maximum drift. Personally, I do it rather more intuitively. I start by saying to myself that there are only 4 drift angles, 0, 5, 10, and 15 degrees, and I will use whichever seems appropriate for my estimate of the wind conditions. So a strong crosswind gets 15 degrees, a strong wind at an angle of about 45 degrees, or a moderate crosswind gets 10 degrees, and for every other crosswind I start with 5 degrees. What I deem to be a strong wind depends on the speed of my aircraft. In my Navajo, only a 50-knot crosswind earns 15 degrees, whereas in a PA-28, a 25-knot wind is enough. I realize that this is all a bit finger in the air, but it's a skill you gradually acquire. If you're starting out, it may be best to work it out using mathematical methods, but soon you'll find it natural. I suppose it's a bit like learning what gear is needed for what speeds in a car. Useful when you start driving, but soon forgotten with experience. But whichever method you use to estimate your initial drift, I do recommend that you err on the side of more allowance for drift. If you end up too far into wind, it's much easier to drift back onto track than if you end up downwind and have to fight your way back. On the RBI or RMI, if you were to turn the aircraft so that the needle points straight ahead and fly this heading, it will only track correctly for a moment until the wind affects the aircraft's track. This technique will result in homing towards the beacon, with constant small heading changes resulting in a curved flight path that eventually arrives at the beacon directly into wind. This is both inefficient in terms of flight path and means that the aircraft's eventual arrival at the beacon is on a different track and heading from that initially planned. E.g., in this example, flying east towards a beacon with a stiff breeze from the north will result in the aircraft arriving at the beacon from the south. As I said just now, you can calculate or approximate the correct heading, but I prefer and teach a more intuitive method. The more intuitive way is to remember that the head of the needle will fall to the tail of the aircraft. This is true whether you're tracking towards or away from the beacon. Using this method, you look at where the needle is. Let's say it's 5 degrees to the left of where you want it. So you want it to fall to the right. You know that to make it fall to the right, it needs to be the right of the nose. So it falls right towards the tail. So you turn left to put it to the right of the nose, and it will fall away. When it's nearly where you want it, you turn back to the right, but not as far as you turned left, so that the new heading maintains track. How far you turn depends on the distance from the fix. But if you're doing it intuitively, you get an idea of that from how fast it responds. If it's moving too slowly for your requirements, you just turn further away. It's quite difficult to teach this intuition, but once you've got it, it's much easier than calculations. Of course, DME or GNSS distance from the fix can be very helpful. Flying away from the fix, I prefer to think about it in terms of radials. The ADF says that I'm on the 080 radial. I want to be on the 090 radial. So it's obvious that I have to turn right to be on a higher number radial. Except for the special case of passing through north, it works beautifully with very little brain power. When using the CDI to track towards a fix, initially the CDI should be centered with the required track by aligning that track with the index at the top of the OBS card or turning the eHSI track pointer to the required track. Say the track towards the beacon is 090 degrees and the wind velocity is 360 at 20, and thus at 120 knots the maximum drift is 10 degrees and, given the wind is a beam, the aircraft will be subject to all 10 degrees of drift. So you set a heading into wind of 080 degrees in the hope that this will result in a constant track made good of 090 degrees. On the HSI, the remote compass-driven backplate displays your heading of 080 and the track pointer indicates that you're on your desired track of 090 with 3 sections of the CDI completely aligned. If after a period of experimentation, you discover that even though you're maintaining an accurate heading of 080 degrees, the CDI is moving to the left. On the HSI, only the center section will move. Then you need to turn to the left to compensate more for the wind because the estimated speed and/or direction was in error. Unlike the single needle tracking described above, a change in heading will not result in an immediate change of relative bearing displayed, but will result in an arresting of any further movement of the CDI to the right, or, given sufficient heading change, will start to move the CDI back to the center. The amount by which you change your heading will depend on the distance from the VOR beacon or the sensitivity of the GNSS. On the VOR, if the distance is more than 15 nautical miles, you may need to correct heading by 10 degrees. If closer, then a turn of 5 degrees would be more appropriate. If on the GNSS you are on a 5 nautical mile sensitivity, which you will only see on older models, you might want to adjust by 10 degrees and maybe 5 degrees for 2 nautical mile and 1 nautical mile sensitivities. Turning too little when distant from the beacon will mean it takes longer to assess the effect of the wind on the new heading and an inefficient track. But turning too much when closer to the beacon will mean too little time to assess the effect of wind and the tendency to overcompensate, resulting in the CDI passing through the center and thus having to recorrect once again, resulting in chasing the deviation. However, arriving on track quickly is probably better than taking a long time if you accept the penalty of needing to keep the CDI in your scan. When the CDI is recentered, you need to adjust your heading back to ensure that you stay on track. Half the previous turn is probably the best guess. This is exactly the same as the dead reckoning you learned as a basic PPL, where you were taught to reverse double the error, then halve it back again. Do you remember how, if you found you were 5 degrees off course to the right, you would change heading 10 degrees to the left, then when you were back on course, adjust 5 degrees to the right? Well, what you're doing on the CDI is the same. If, after the first adjustment, the CDI is still slowly going off track, you need to make a further adjustment, but make it by a smaller amount, maybe 4 degrees towards the track, then 2 degrees back. Of course, if your navigator has an actual track pointer or a digital readout of track, then your life is simpler. Once on track, choose the heading that keeps the track pointer in place on the desired track, or keeps the digital readout of track reading the desired track. Once you have this heading, set the bug. This allows you to take a more relaxed attitude to the crosswind. If we track into a VOR and directly overhead, the CDI will centralize, an unreliable signal nav warning flag will be displayed, and the direction flag will flicker or, in the case of the eHSI, disappear. As the aircraft passes through the overhead, called the cone of uncertainty or the cone of confusion, the flag will change from to from, and the nav flag will disappear. But in reality, it's impossible to make an absolutely perfect beacon crossing. The aircraft will always be a little off to one side. So this close to the VOR, the CDI will show full-scale deflection. If you keep your nerve and maintain the same heading tracking away from the beacon, you'll notice that the CDI will move back to the center. Tracking is made hugely easier with an eHSI or glass display because it shows a track pointer. In this example, it's a cyan diamond, but different units have different colored diamonds. This shows the actual track being flown. In this case, the heading is 276 degrees, but the track is 265 degrees. Here, the course pointer is on 265 degrees and the CDI is centralized. If you keep the track pointer on the end of the course pointer, then the aircraft is tracking along the desired course and the CDI cannot move. If the CDI does move, then the aircraft should be turned so that the track pointer is the same side of the course pointer as the CDI. When the CDI is back in the middle, the aircraft is turned back to put the track pointer at the end of the course pointer. The same technique can be used on a single needle, whether pointing at an NDB, VOR or GNSS waypoint. If you put the track pointer on the end of the needle will not move. People do get confused about which way the track pointer is going to turn. If you want it to turn right, you turn right and vice versa. Finally, let's think about intercepting a desired track towards or from a fix. The first thing you need to do is to visualize the requirement. This can be done by drawing on paper or a moving map, or, if you have one, a chart. If you have a moving map, this will give you excellent situational awareness. If you have an eHSI, that is an excellent aid to visualization. You should set the eHSI to the required track so that you both have a feeling for the maneuver required and an easy reference for when the ADF is approaching alignment and is aligned. Say you want to intercept a track into a fix, let's say 260 degrees inbound, and you are approaching from the southwest heading 030 degrees. If you have one, you change the eHSI track pointer to 260 degrees. Because you need the needle to fall to the left, you need to get it to the left of the nose. So let's say you fly 060 degrees and watch the progress of the needle falling away towards 260 degrees, which is now 170 degrees to the left of the nose. As you watch the progress of the pointer, you decide if it's falling fast enough. If not, you need to turn further right. As the needle approaches 260 degrees, which you can most easily see from the eHSI if you have one, you start the turn towards it, but always keeping it to the left of the nose so it keeps falling to the tail. Take your turn in chunks so that you're reducing the angle to the desired track in a manageable way. Notice that once you're established, the ADF needle exactly overlays the eHSI. Intercepting a track away from the fix is similar, except that you're allowing the needle to fall towards the tail until it shows that you're on the correct outbound track. Ironically, interception is rather more challenging using a CDI than using a single pointer, particularly if you don't have an eHSI, because, as I said earlier, the CDI instrument will indicate your position only if you're within 10 degrees of the selected radial. Because you don't have a needle pointed towards the fix, you have to find your current track to the fix by centralizing the CDI with the two flags showing, then building a mental model of an initial heading towards a reasonable interception point and set that heading. For the inexperienced, this is best done as a sketch on paper. Once that heading is set up, this is where the eHSI comes into its own, as it is quick and intuitive to check the current radial and when you are getting close to the desired track. As you approach the desired track, set the OBS or eHSI onto that track. You should gradually reduce the interception angle so there is little chance that you'll pass through the track. It is better to intercept a little later than have to correct back on track, which is effectively starting the exercise again from the other side. If you're flying into wind, you should turn later, and if a tailwind, earlier, to allow for the effect on the radius of turn. You can use the eHSI lubber line to touch the end of the CDI to give a smooth turn onto the heading required to maintain the track, remembering to use a heading which allows for drift when you do intercept. If you're using a glass eHSI, it's very helpful to keep the top of the CDI aligned with the track pointer diamond, and this will turn you neatly onto a wind-corrected heading that maintains track. Some eHSIs are provided with a dotted line for this purpose. The OBS is less helpful in this regard, and it may be a good idea to keep the paper sketch going while you check your position by recentering the CDI. Once you're close to the desired track, set up an initial intercept angle of about 45 degrees, reducing that to 30 degrees as the needle starts to move. Then gradually reduce that intercept angle as the needle centers, again being sure to use a heading which allows for drift when you do intercept. If you have a moving map displaying the desired track you want to intercept, then you may choose to be more aggressive about the intercept angle so as to get onto the known track more quickly, in which case a 90-degree intercept can be chosen initially, reducing the intercept to about 40 degrees when the CDI starts to move, and holding this intercept until 1 dot from centered, only then turning onto a heading to maintain the desired track. The moving map allows you to see how far from the intercept you are, so it allows you to scan to CDI eHSI at a reasonable rate. Remember, all IFR turns are at rate 1. If it looks like you're going to go through the desired track, do not tighten the turn, you just have to keep the turn going to re-intercept. I've never found a theoretical method that's ideal, but rely on practice, most usefully on a simulator when you can set up the wind conditions you want to practice with. And with more experience, this becomes intuitive. So, that's a quick run through tracking and intercepting NDB, VOR and GNSS tracks using RBI, RMI, OBS and HSI. I hope you found it helpful. See you in the next video.